Now let's talk about uniform circular motion. An object moving in a circle with a constant speed is said to undergo a uniform circular motion. So for example, in this picture, if an object is going around and around in a circle, it is said to be undergoing a uniform circular motion. So object is moving at a constant speed. Its position is given by a vector r, and say its velocity is given by a vector v. The instantaneous velocity of this object will always be tangential to its motion. The instantaneous acceleration of this object is going to be perpendicular always to the velocity vector. Now, even though that this ball is supposed to be moving at a constant velocity, it is being accelerated. So remember, these are vector quantities. So if the velocity is a vector and acceleration is also a vector, even though the magnitude remains the same, but it is accelerating because of the change of direction. Acceleration for a uniform circular motion, the acceleration is always going to be towards the center of the circle. That is why the acceleration is called radial acceleration or centripetal acceleration, which basically means is center seeking. So a centripetal acceleration is given by this formula, A equals v squared over r. Now let's go ahead and see where this formula is coming from. It's not just coming from a random thing, but there is actually equations that we've used in order to derive these. So in order to derive these, we are going to start with speed equals distance over time formula. Okay? So when things move in a circle, in order for me to start from this point and come back to this point again, how much distance did I cover? 2 pi r, right? If r is the radius and I covered the whole distance, I covered 2 pi r, the amount of distance, divided by time. So when things move in a circle, we call it a period, right? Capital T. So this time for something to move in a circle is going to be called period. And I'm going to call speed as v. So one formula is speed equals 2 pi r over t. Now this does not still look like that centripetal acceleration formula. However, what I can do is I can take the derivative with respect to t on both sides. So I can rewrite this equation as vt equals 2 pi r, and I could do dv by dt times t equals 2 pi dr by dt. Okay, what is dv by dt? Acceleration. T is just a number because it's for the whole circle, equals 2 pi v. Okay, so it's going to be at equals 2 pi v. Here's another formula that we got. Okay, so now I can have this expression. I'm going to call this expression 1, and I'm going to call this expression 2. And from expression 1 and expression 2, I can find what t is, right? So if I'm to rewrite these two expressions, I can rewrite them as t equals 2 pi r over v from this equation. And from this one, I can rewrite t equals 2 pi v over a. Since these both are t's and therefore the same expression, I can rewrite this as 2 pi r over v equals 2 pi v over a. Correct? 2 pi goes away. So then I will get a, actually, so let me write it in another way. So r equals v squared over a. And that means a equals v squared over r. So this is that formula that we were just talking about, right? Another interesting thing that we can do with this formula, which is now going to be my centripetal force, centripetal acceleration formula, is what happens when I multiply both sides with m. So let's say I multiply both sides with m. What's that equation? Absolutely. That is sigma f. So sigma f could also be written as m squared over r. Good? And this is going to be our centripetal force expression that we will see in a second. So for a uniform circular motion, Newton's laws are going to be rewritten as sigma f, c, which is for centripetal, equals mac. But here the subscript will mean radial force and radial acceleration. So this force is now going to be called the centripetal or the center-seeking force. Now the easiest example to give is for a mass attached to a string. This centripetal force is provided by the tension in that spring. So in order for this to work, our equation, our Newton's laws, is going to change slightly. So this force, that is our centripetal force, is going to be provided by the tension in the spring. So we can write T equals mv squared over r, or sigma fc. Okay? So note, as the ball moves around, which is attached to a spring, the acceleration and the centripetal force are directed inwards towards the center, whereas the ball and the motion of the ball is around this circular path. And the velocity vector v is always going to be tangential to the motion, just like shown here. Now the interesting part is, what if you cut the string? What happens when you cut the string? So note very carefully, once the string is cut, the object will move in a straight line away from it along a tangential path. So this is very careful. Note this very carefully. Similarly, for an object moving, say for example, if you were in a car and the object was allowed to be free and allowed to be moving, then this object will continue to move in a straight line. The only way for us to make sure that the object and the car stay together is to find some kind of a resistive force on the side so that it hits it, but it doesn't move away. Okay? A few misconceptions that I know we all have. One of them that I've been asked for a while is, shouldn't there be an outward force pulling the ball out that is opposite to the tangential force or the centripetal force in that direction? And the answer is no, absolutely not. There is no force that's acting outwards for a mass attached to a spring. The other misconception is, what about centrifugal force that is supposed to point outwards that I feel when my car goes around a high-speed curve? And the answer is, in physics, there is no such thing as a centrifugal force. There never is. Centrifugal force, the concept came about is when engineers talk about a coordinate system. It helps them to make Newton's laws work. And so they have to invent a pseudo force, which is not really a force, which they call centrifugal force. Okay? So then you should ask me, but what about the force that I actually feel when my car goes around the curve at a high speed? Well, it is definitely not centrifugal force. It is just the centripetal force of the door pushing you towards the center of the turn in the center of the circle in that particular turn. And your brain interprets this effect of Newton's first law as a force pushing you outwards. It is still a force that's acting inwards. So these are very clear misconceptions that people have about motion in a circle. So don't get confused. Another factor is what happens when you have different kinds of masses and they're going at a different velocity. So for example, if you have a smaller mass, you will need a smaller centripetal force in order to keep it moving in a circle. If you have a smaller velocity, then that means you will still need a smaller force in order to keep moving it in a circle. If you have a smaller length, however, you will need a larger force in order to keep it moving in a circular path. Note also again here, acceleration, centripetal acceleration and centripetal force are always going to point towards the center, and they are always going to point in the same direction while we're going in a circle. And note, velocity vector, no matter which of the three I'm looking at, is always going to be pointing towards the tangent. Here's a really good example. So, for example, in here, there is a tire rotating and there is a mud. There's mud on the floor, and this mud wants to stick to the wheel of the car. So in both of these scenarios, which one will it stick to? One is faster moving car, and the other one is not so fast moving car, right? So a faster moving car will get rid of its mud faster, right? Now my next question for you is that a rock is being whirled at the end of a string in a clockwise direction. If the string breaks, the path that the rock will follow is A, B, C, or D. Knowing what you know about centripetal force, you should be able to answer this very quickly. And the answer is absolutely path C, right? It cannot follow any other path. The velocity vector is always going to be along the tangent, and if it is going in a clockwise direction, it is going to point towards the path C. Very good.